This is not a story of sudden catastrophe, but of a long, slow decline, a fading of cosmic light that began long before we were here to notice it. It is a journey that will take us from the fiery birth of the first stars to the silent tombs of galaxies that no longer give rise to new suns. It is also a journey into our own place in time, revealing that we live not in the bright youth of the cosmos, but in its long twilight. Before we can grasp this truth, we must step into history, to a darkened gymnasium in Stockholm in the year 1940, where a Swedish physicist set out to watch millions of years of cosmic history unfold before his eyes. This is not a story of sudden catastrophe, but of a long, slow decline, a fading of cosmic light that began long before we were here to notice it. It is a journey that will take us from the fiery birth of the first stars to the silent tombs of galaxies that no longer give rise to new suns. It is also a journey into our own place in time, revealing that we live not in the bright youth of the cosmos, but in its long twilight. Before we can grasp this truth, we must step into history, to a darkened gymnasium in Stockholm in the year 1940, where a Swedish physicist set out to watch millions of years of cosmic history unfold before his eyes. In the year 1940, in the heart of Stockholm, a Swedish physicist named Erik Holberg set out to answer a question that most would have dismissed as impossible. At a time when our understanding of the universe was still in its infancy, Holberg dared to believe that he could watch cosmic history unfold within the walls of a simple gymnasium. His laboratory was not a towering observatory or a mountaintop telescope, but a large, dimly lit hall with a polished wooden floor. Here, he sought to capture the slow, grand dance of galaxies, to compress millions of years of celestial evolution into something the human eye could witness. Holberg's idea was simple, yet profoundly elegant. He placed 74 stations across the gymnasium floor, each representing a portion of a galaxy. At every station stood a bright electric bulb and a photoreceptor, linked together so that each could sense the light from all the others. The light stood in for the pull of gravity, its strength decreasing with distance, just as the real force of gravity does. Each bulb was a stand-in for an immense pocket of mass, a tiny fragment of a galaxy that could influence its neighbors and be influenced in return. During cosmic noon, the rate of star formation was many times higher than it is today. Some galaxies gave birth to hundreds of new stars every single year, filling their arms and halos with hot, blue giants that lived fast and died young. The sheer scale of this activity transformed the cosmic landscape. Vast star-forming regions glowed like beacons across millions of light years, while supernova explosions seeded space with heavier elements, preparing the way for planets, oceans, and perhaps even life in the distant future. It was, in essence, the first analog simulation of the cosmos. Instead of mathematical equations locked away in a notebook, Holberg's model was tangible, visible, and alive with light. As he advanced the simulation through imaginary centuries and eons, the two galaxies reached toward each other, their graceful spiral arms distorting under mutual gravity. He watched them stretch and twist, tidal tails unfurling like ribbons across the floor. Beauty and physics intertwined in a way that was both artistic and scientific. Yet beyond the beauty, Holberg saw something deeper. In the careful arrangement of bulbs and sensors, he witnessed the life cycle of galaxies themselves. He saw how collisions could reshape them, how their forms could be torn apart, and how eventually they could fade. This was not the eternal, unchanging universe many once imagined. This was a cosmos in motion, a cosmos where even the most magnificent structures had a finite lifetime. The galaxies we know and admire today, he realized, would not endure forever. In that shadow-filled gymnasium, Holberg had captured more than a scientific demonstration. He had given us a vision of impermanence, a glimpse of a universe that is constantly changing and constantly aging. What he could not know, lacking the powerful instruments and simulations of our time, was that the wider cosmos had already passed its most vibrant age. Much of it was already in decline, moving slowly toward a distant and inevitable darkness. His humble experiment would plant a seed, an idea that would grow in the decades to come, reshaping our understanding of the universe's past, present, and future. The universe that we see today, with its sweeping spiral galaxies and glittering clusters of stars, is only the latest chapter in a much older story. In its earliest moments, the cosmos was a place so alien that it would be unrecognizable to us. There was no light, no planets, no stars, and not even the familiar atoms that make up our bodies and our world. Instead, it was filled with a seething ocean of energy, a hot and dense state where matter and radiation were one and the same. In those first fractions of a second, the laws of nature forged the blueprint for everything that would follow. As the newborn universe expanded and cooled, it began to produce its first particles. In those ancient instants, exotic entities may have formed, such as magnetic monopoles or cosmic strings, relics of a primordial physics unlike anything we can recreate today. If they ever existed, they have long since vanished, erased by the relentless march of time. Just minutes after its birth, the universe cooled enough for protons and neutrons to combine, creating hydrogen, helium, and trace amounts of other light elements. These elements, simple yet vital, would become the foundation for all future stars and planets. For hundreds of thousands of years, the cosmos remained a featureless expanse of scorching plasma. Photons of light could not travel freely, trapped in constant collisions with particles. But as the temperature fell to around 10,000 degrees Kelvin, protons and electrons bound together to form neutral atoms. This transition released an ocean of light that has been traveling ever since. The cosmic microwave background. It is the faint afterglow of creation, a one-time event that marked the end of the universe's first chapter and the beginning of a new era. Even after this moment of clarity, the universe lay in darkness. There were no stars to shine, no galaxies to give structure. This period, known as the Cosmic Dark Ages, lasted until gravity gathered the first great clouds of hydrogen and helium into dense knots. In these knots, the crushing pressure ignited nuclear fusion, and the first stars were born. They were giants, far more massive than most stars today, burning hot and bright for only a few million years before exploding in titanic supernovae, scattering heavier elements into the void. From these stellar deaths came enrichment. The gas between the stars now carried carbon, oxygen, iron, and other ingredients essential for life. Galaxies began to assemble, drawn together along the invisible threads of the cosmic web. Collisions between these young galaxies were frequent, chaotic events that triggered storms of star formation. Slowly, the universe transformed from a dark, diffuse expanse into a richly structured tapestry filled with light. Vast clusters of galaxies emerged at the intersections of cosmic filaments, while immense voids yawned between them. By the time the universe was a few billion years old, it had reached what astronomers call cosmic noon, the peak of star formation. Galaxies converted their gas into new suns at furious rates, 10 times faster than they do today. In this era, the sky of any inhabited world would have been ablaze with starlight, far richer and more crowded than the skies we know. Yet even at its height, this golden age could not last. The same processes that fed the birth of stars also began to exhaust the fuel needed to sustain them. Over the billions of years that followed, the universe gradually shifted into a slower rhythm. Star formation declined, galaxies matured, and the brilliant chaos of the early cosmos gave way to a more settled grandeur. Our own Milky Way, like many others, built its spiral arms during this period, gathering stars, planets, and clouds of dust into graceful order. But the past remains written in the light of the most distant galaxies, telling us that the universe we inhabit today is only one stage in a vast and ongoing transformation, a transformation that will carry on long after our time. In the early decades of the 20th century, many astronomers still believed that the Milky Way contained the entire universe. The faint spiral shapes glimpsed through telescopes were thought to be small clouds of gas within our own galaxy. Then came Edwin Hubble. By studying the light from these mysterious spirals, he proved that they were, in fact, vast galaxies far beyond the Milky Way. Even more astonishing, his measurements showed that these galaxies were all moving away from us, revealing for the first time that the universe itself was expanding. Hubble's work transformed the scale of the cosmos overnight. The known universe grew from hundreds of thousands of light-years across to hundreds of millions. In the decades that followed, better telescopes and new methods of measuring distance pushed this frontier further still. By the mid-1950s, astronomers were estimating distances of billions of light-years. Each improvement was like peeling back another layer of time, allowing humanity to see deeper into the past, when galaxies were younger and the universe itself was still finding its shape. Then, in the late 1950s, a new mystery emerged. Radio surveys of the sky revealed incredibly bright sources of energy that looked like faint stars in visible light. Astronomers called them quasi-stellar objects, or quasars. They shone with the energy of 1,000,000 galaxies, yet they were compact enough to appear as single points of light. Their most striking feature was their distance. All known quasars lay billions of light years away, meaning they existed in a much younger universe. None were found nearby, a clue that these objects belong to a vanished cosmic era. The discovery of quasars proved that the universe was not static in its details, but evolving dramatically over time. Whatever conditions had allowed quasars to form no longer existed in the present day. To explain their power, astronomers would eventually link them to supermassive black holes feeding on surrounding matter. But even before this connection was made, quasars had already deepened the shock begun by Hubble's findings. They told us that the distant universe was not only farther than we had ever imagined, but profoundly different from the one we see around us now. The most distant quasars discovered in the early years were more than 12 billion light-years away, their light beginning its journey when the universe was less than 1 billion years old. These were beacons from a formative age, powered by supermassive black holes swallowing vast amounts of matter. The conditions that created them were rare and fleeting, tied to an era when galaxies were young and rich in gas. Their absence in the modern universe is a reminder that we are looking back at a time that can never return, a time when cosmic energy burned with unmatched intensity. To see even further into that vanished past, astronomers needed a new kind of eye. The James Webb Space Telescope was built to observe in the infrared, able to pierce through cosmic dust and capture light stretched by the universe's expansion. From its position beyond the Moon's orbit, Webb can reveal galaxies so distant that their light has traveled for almost the entire history of time. It offers not only sharper images, but also the ability to study the chemistry and motion of these early systems, uncovering the building blocks of cosmic structure. Among Webb's most striking discoveries are small, faint galaxies from only a few 100 million years after the Big Bang. Some, like the galaxy labeled Z14, are unexpectedly large and filled with newborn stars. Their sizes rival that of the small Magellanic Cloud, suggesting that in just a short span of cosmic time, they could grow into giants. Webb's deep surveys also reveal the earliest threads of the cosmic web, the great network of filaments and clusters that would take billions of years to form the intricate structure we see today. The journey from Hubble's first revelations to Webb's unprecedented views has transformed our understanding of the universe. Hubble showed us that space was vast and dynamic. Quasars revealed that the early universe was a place of extraordinary activity, unlike anything in our era. Webb now allows us to witness those ancient scenes directly, seeing the first galaxies take shape. Together, these discoveries remind us that the cosmos is not a static backdrop, but a living history connecting the distant past to the moment we inhabit now. There was a time in the universe's history when the birth of stars reached its peak, a period astronomers call cosmic noon. It occurred several billion years after the Big Bang, when the cosmos was still young and overflowing with raw material. Galaxies were smaller, closer together, and bursting with activity. Everywhere, from the dense cores of spirals to the chaotic forms of irregular galaxies, new stars ignited in staggering numbers. It was a golden age of creation, when the universe shone with its brightest and most abundant light. During cosmic noon, the rate of star formation was many times higher than it is today. Some galaxies gave birth to hundreds of new stars every single year, filling their arms and halos with hot, blue giants that lived fast and died young. The sheer scale of this activity transformed the cosmic landscape. Vast star-forming regions glowed like beacons across millions of light years, while supernova explosions seeded space with heavier elements, preparing the way for planets, oceans, and perhaps even life in the distant future. This extraordinary pace was driven by the universe's youth. Enormous rivers of gas flowed along the filaments of the cosmic web, pouring into galaxies and feeding their growth. Frequent collisions and mergers between galaxies triggered shock waves that collapsed gas clouds into dense knots, the cradles of newborn stars. Dust, forged in the deaths of earlier generations, cooled these clouds, allowing gravity to take over. It was a perfect storm of abundance, compression, and cooling, a combination of conditions that no longer exists in the calmer, quieter universe we see around us today. This extraordinary pace was driven by the universe's youth. Enormous rivers of gas flowed along the filaments of the cosmic web, pouring into galaxies and feeding their growth. Frequent collisions and mergers between galaxies triggered shock waves that collapsed gas clouds into dense knots, the cradles of newborn stars. Dust, forged in the deaths of earlier generations, cooled these clouds, allowing gravity to take over. It was a perfect storm of abundance, compression, and cooling, a combination of conditions that no longer exists in the calmer, quieter universe we see around us today. In the age of cosmic noon, the largest galaxies were true engines of creation. Their immense gravitational wells drew in endless streams of gas, fueling star factories on a colossal scale. These giants gave rise to the most massive stars, the kind that ended their lives in brilliant supernovae and left behind black holes of staggering size. Their influence reached far beyond their own spiral arms, shaping the structure of surrounding space. They were the architects of the great galaxy clusters that would continue to dominate the universe for billions of years. Yet, it was not only the giants that defined this era. The universe was filled with countless dwarf galaxies, far smaller in size but fierce in their activity. These compact systems burned through their reservoirs of gas quickly, forming stars at rates that rivaled or even surpassed their larger cousins. Many of these dwarfs would later merge into larger galaxies, donating their stars and enriching their hosts with heavy elements. In their brief but intense lives, they acted as sparks in the grand fire of cosmic noon, adding to the brilliance of the epoch. The legacy of cosmic noon is written across the universe we see today. The heavy elements produced during this period became the raw material for rocky planets, moons, and the chemistry of life. The immense stellar populations built during this time would go on to form the spiral arms, globular clusters, and central bulges of galaxies. Even the quiet stability of our own Milky Way is the result of foundations laid during that cosmic peak. Without the abundance of stars and metals forged in this era, the universe would be a far poorer, dimmer place. But like all seasons, cosmic noon could not last. Over time, the rivers of cold gas began to thin. Galactic mergers became less frequent, and the energy from supernovae and black holes heated the surrounding gas, making it harder for new stars to form. Slowly, the universe shifted into what astronomers call the cosmic afternoon, a calmer period where star birth still continued, but at a fraction of its former pace. The dazzling fireworks of creation dimmed, and the cosmos began its long, graceful slide into the quieter twilight we inhabit today. After the brilliance of cosmic noon, the universe began to change. The great rivers of creation that once fed galaxies with fresh material started to slow. Astronomers call this the cosmic afternoon, a time when star formation still continued, but at a far gentler pace. With each passing billion years, the fireworks of creation faded. Eventually, this would give way to the cosmic evening, an age of calm and maturity, where most galaxies would settle into quiet shapes, no longer forging stars with the same fevered energy of their youth. The signs of decline are written across the night sky. Where once young, blue galaxies blazed with the light of countless newborn stars, now many have turned red, their stellar populations aged and cool. The vast star-forming regions that once lit up spiral arms have become rarer, confined to a few scattered nebulae. Large surveys of the cosmos reveal fewer bright starburst galaxies and more that are dim, quiescent, and stable. The universe has begun its long transition from a place of restless creation to one of lasting endurance. A primary reason for this slowdown lies in the loss of cold gas, the raw fuel of star formation. In the early universe, enormous flows of hydrogen streamed along the filaments of the cosmic web, pouring into galaxies. But as time passed, these supplies thinned. Some of the gas was consumed in earlier bursts of star creation. Some was heated by stellar winds or supernovae, preventing it from cooling and condensing into new stars. As the universe expanded, the infall of fresh gas slowed, leaving many galaxies starved of the material they needed to sustain their growth. At the heart of nearly every large galaxy lies a supermassive black hole. For most of a galaxy's life, it remains quiet, exerting its influence only through gravity. But when fed with an abundance of gas, it can awaken in spectacular fashion. As matter spirals inward, it forms a blazing accretion disk, heating to extreme temperatures and unleashing torrents of radiation. This energy can sweep through a galaxy, heating vast clouds of gas and halting their collapse, effectively shutting down star formation across entire regions. In some cases, the black hole's fury is channeled into narrow jets of plasma, racing out from its poles at nearly the speed of light. These jets can pierce thousands of light years through the galaxy, ejecting gas into intergalactic space. Once expelled, this precious fuel cannot return. Major galactic mergers often trigger such outbursts, briefly feeding the central black hole with a feast of matter. The result is both magnificent and fatal. The very forces that once encouraged star birth now act to end it, turning vibrant galaxies into silent, fading relics of their former selves. Galaxies do not always drift alone in the silent dark. Many live in dense clusters containing hundreds or even thousands of neighbors, bound together by gravity. Between these galaxies lies a thin but scorching plasma, heated to tens of millions of degrees. When a galaxy plunges into such an environment, the motion through this hot medium exerts a powerful drag on its own gas. This process, called ram pressure stripping, can peel away vast streams of cold gas from a galaxy's disk, leaving behind long tails that stretch for tens of thousands of light years. These so-called jellyfish galaxies are striking to behold, their luminous trails marking the path of stripped material. But the beauty hides a fatal truth. Once the cold gas is torn away, the galaxy is deprived of the very substance it needs to form new stars. Star formation slows, then stops entirely. In a crowded cluster, this fate is common. The combined effects of heating, stripping, and gravitational interactions with neighboring galaxies turn once vibrant spirals into dim, quiescent systems, adding to the growing population of red and dead galaxies that dominate the modern universe. Our own Milky Way still stands among the more active galaxies of this age, producing around 7 new stars each year. Yet, even here, the signs of change are evident. The great reservoirs of cold gas in the outer disk are not infinite, and the streams of material from intergalactic space are weaker than they once were. In a few billion years, the Milky Way will collide and merge with the Andromeda Galaxy. This event will ignite a brief, spectacular burst of star formation, but after the fireworks fade, the combined system will begin its slow decline into quiescence. The cosmic evening marks the final phase of the universe's fertile life. In this era, most galaxies have exhausted or lost their cold gas, and the formation of new stars is a rare event. The cosmic web remains in place, vast and intricate, but its great intersections no longer blaze with the energy of creation. Instead, the universe is filled with mature galaxies glowing softly with the light of older, cooler stars. It is a time of stability, when the grand structures of the cosmos endure, but their inner vitality fades. This long twilight is more than the slow fading of light. It is the closing of a unique chapter in cosmic history. The conditions that nurture life as we know it, plentiful heavy elements, active star formation, and stable planetary systems, may only exist for a brief window on the universal timescale. We are fortunate to live within that window, in a universe still rich enough to sustain creation, yet old enough to have forged the worlds and elements that make us possible. The cosmic evening is a reminder that even cosmic beauty is fleeting, and that our moment beneath the stars is precious. In the life of every galaxy, there comes a time when the birth of new stars slows, then stops entirely. Astronomers call this process quenching, a term that captures the sense of a flame being extinguished. It is not the result of a single dramatic event, but the outcome of many interacting forces. Over millions or billions of years, a galaxy that was once blue and bright, with the light of young stars, will fade to a soft, reddish glow. In the end, every galaxy will pass through this stage, leaving behind only the remnants of a more active past. Galaxies in the midst of quenching reveal themselves in subtle but telling ways. The bright blue light of hot, massive stars begins to vanish, replaced by the cooler tones of older, smaller stars. Vast star-forming regions that once lit up the spiral arms shrink or disappear entirely. The spectrum of the galaxy's light shifts toward the red, a sign that no new stars are being born. Seen from afar, such a galaxy may still appear majestic in shape, but it has entered a quieter phase, no longer building the next generation of suns. One pathway to quenching begins with an excess of creation. In a starburst event, a galaxy forms stars at an extraordinary rate, sometimes thousands of giant stars at once. These massive stars live short, brilliant lives, and during their brief existence, they pour out streams of high-energy particles and intense radiation. These stellar winds sweep through the surrounding gas, heating it and driving it away from the dense regions where stars are born. Without cool, collapsing gas clouds, the star-making machinery grinds to a halt. The deaths of massive stars can also hasten the end. When many of them explode as supernovae within a short span of time, the combined shockwaves ripple through the galaxy, breaking apart clouds of gas and ejecting material into interstellar space. These explosions carve vast cavities, or bubbles, in the galactic medium, erasing the dense pockets where new stars could have formed. In extreme cases, this loss of star-forming material can last for millions of years, preventing the galaxy from recovering its former vitality. Perhaps the most powerful agent of quenching lies at the very center of a galaxy. When a supermassive black hole awakens, fed by streams of gas spiraling inward, it becomes a beacon of unimaginable energy. The accretion disk around it blazes, emitting radiation that can heat the galaxy's gas to the point where it can no longer cool and collapse. In many cases, the black hole also launches narrow jets of plasma that punch through the galaxy, flinging gas far into intergalactic space. Once this precious fuel is gone, the galaxy's era of star formation is over. Some galaxies meet their end not in solitude, but in crowded cosmic neighborhoods. Within massive clusters, galaxies swim through a thin but blisteringly hot plasma that fills the space between them. As a galaxy moves at high speed through this medium, the pressure of its motion strips away its own cold gas, peeling it from the disk, like wind tearing leaves from a tree. This process, called ram pressure stripping, leaves behind long, luminous tails of gas and dust. Deprived of its star-making material, the galaxy fades, joining the ranks of the dormant and the red. Even without external violence, a galaxy can simply run out of the fuel it needs to make stars. Over billions of years, its reservoirs of cold hydrogen and helium are steadily consumed. If no fresh material flows in from intergalactic space, the star-forming regions shrink, then vanish. In the early universe, rivers of gas streamed along the filaments of the cosmic web, replenishing galaxies and keeping them active. But as the cosmos ages and expands, these flows weaken. For many galaxies, the end comes quietly, as the fires of creation sputter and die through simple exhaustion. When quenching is complete, a galaxy is transformed. The brilliant blue light of hot young stars is gone, replaced by the steady, amber glow of older populations. Only small, dim red dwarfs remain in abundance, along with the cold corpses of white dwarfs, neutron stars, and black holes. The grand spiral arms that once teemed with activity become quiet and ghostly. To an outside observer, such a galaxy might still appear vast and elegant, but its days of building new suns are over. It has become a relic, a monument to a more active and luminous age. Quenching is not a rare accident, but the natural destiny of all galaxies. It marks the closing act of the stellar cycle and signals the slow dimming of the cosmos itself. The window of time in which abundant star formation, heavy element production, and planetary system creation can occur is brief on cosmic scales. We happen to live within that window, in a galaxy still rich with star-forming gas. But the future is written. Eventually, even the Milky Way will join the silent graveyard of red and dead galaxies as the universe drifts into its long and final night. In 1940, Swedish physicist Erik Holberg recreated the slow dance of galaxies with nothing more than light bulbs, photosensors, and a gymnasium floor. His pioneering experiment was a glimpse into cosmic motion, built with the tools of his time. Today, that spirit of simulation lives on, but the scale has changed beyond recognition. The gymnasium has been replaced by vast halls filled with supercomputers, their processors working in perfect synchrony to compress billions of years of cosmic history into hours of calculation, revealing the hidden patterns of the universe. Among the most advanced of these digital universes is a project known as Illustris, the next generation. It uses nearly 100,000 computer cores working together to simulate a small but detailed fraction of the observable cosmos. Every galaxy in the model grows and evolves under the pull of gravity, the flow of intergalactic gas, the shock waves of exploding stars, and the powerful influence of supermassive black holes. What began as equations on a page becomes, through this simulation, a living, changing replica of the universe itself. The aim is not only to produce a beautiful visual echo of the universe, but to understand it. These simulations allow scientists to track the flow of gas as it cools and condenses into stars, to follow the assembly of galaxies, and to witness the rise and slow decline of cosmic structure. By comparing the simulated universe to observations from telescopes such as Hubble, James Webb, and ALMA, astronomers can refine their models, testing which physical laws and processes truly shape the universe across billions of years. When set to the earliest epochs, the simulation reveals a universe still in its infancy, only a few 100 million years after the Big Bang. The first galaxies appear as small, faint islands of light, adrift in vast darkness. They feed on cold streams of gas flowing along the filaments of the cosmic web, growing quickly in mass and brightness. The simulation shows them merging, colliding, and sparking intense bursts of star formation, painting a vivid portrait of a cosmos awakening from its long, dark age into a landscape rich with newborn light. The predictions of these vast simulations find their test in the night sky. The James Webb Space Telescope peers deep into cosmic history, capturing the faint glow of galaxies that formed when the universe was still young. Many of these match the shapes, sizes, and clustering patterns seen in Illustris TNG, as if the model and the real cosmos were speaking the same language. At the same time, the ALMA Observatory maps the cold gas reservoirs of distant galaxies, revealing filaments and protoclusters like SSA-22 that mirror the structures born in the simulations. Alone, observation offers snapshots, beautiful but incomplete frames of an ongoing story. Alone, simulation is only an educated guess, vulnerable to the limits of its assumptions. Together, they become something far more powerful. Observations anchor simulations in reality, while simulations fill in the unseen, the hidden rivers of gas, the long arcs of gravitational evolution that no telescope can watch unfold in real time. This partnership allows scientists to peel back the layers of mystery surrounding how galaxies live, grow, and eventually fade, bringing us closer to the universe's deepest truths. From Holberg's light bulbs to the James Webb's golden mirrors, the journey of simulating and observing the cosmos has become a bridge between the known and the unknown. We now stand on that bridge, looking both backward into the universe's turbulent youth and forward toward its quieter, dimmer future. The models and the evidence together tell a consistent story. The great age of star birth is ending. In the next chapter, we will step into this cosmic afternoon, and explore how the universe's brilliance slowly gives way to an era of stillness. Imagine stepping off the familiar shoreline of the present and plunging into an ocean of time so vast that human history becomes a speck, the age of the stars a single breath. We move forward not by centuries, not by millions of years, but by hundreds of billions. On this scale, mountains erode to dust, continents drift into new shapes, and entire galaxies shift their places in the cosmic web. It is a journey into an era where the universe has aged beyond recognition, and yet it still breathes in its own slow, imperceptible rhythm. Roughly 100 billion years from now, the expansion of space will have pulled all but the closest galaxies beyond the horizon of what can be seen. The great tapestry of cosmic history, now visible through telescopes, will fade into darkness. Future astronomers, no matter how advanced, will see only a small handful of galaxies bound together by gravity. The rest will have vanished from view forever, erased not by destruction, but by the relentless stretching of space, leaving a cosmos that feels smaller, lonelier, and more confined than ours today. As the eons pass, the raw material for making stars will be consumed. Cold hydrogen gas, the lifeblood of stellar birth, will grow scarce. Star formation will slow to a crawl and then cease entirely. The sky will gradually lose its bright young suns, replacing them with ancient dim remnants, white dwarfs, neutron stars, and the occasional black hole. What once was a restless, luminous universe will enter its first long period of stillness, a cosmic afternoon when no new fires are lit, and the existing ones burn lower with each passing age. In this distant era, the Milky Way and Andromeda will have long since merged, forming a single, massive galaxy, sometimes called Milkomeda. Smaller companions, like the Magellanic Clouds, will be absorbed, their stars folded into this vast stellar city. Isolated in the expanding void, this lone galactic island will be the entire observable universe for its inhabitants. The wider cosmos, with its billions of galaxies, will be gone from sight, replaced by an endless sea of black, a reminder that even in the universe's future, beauty and isolation walk hand in hand. In the remote ages of the cosmos, a few massive stars will still be born, blazing into life for brief moments measured in only millions of years. They will burn furiously, ending in cataclysms so bright they will briefly outshine entire galaxies. These final supernovae will be rare jewels in an otherwise dark sky, scattering the last heavy elements into space. But there will be no newborn stars to inherit these riches. The metals will drift forever, unused, across a universe that has already closed its age of creation. As the starlight fades, countless worlds will drift unmoored, ejected from their birthplaces, or abandoned after their suns die. These rogue planets will roam through an ocean of darkness, lit only by their own fading heat or the faint shimmer of auroras. To stand upon such a world would be to stand in endless night. No sunrise, no guiding constellations, only the cold silence of space and the faint, unreachable glow of ancient galaxies retreating beyond the horizon of sight. This will be the beginning of the universe's deep night. With no more stellar fire, energy will grow scarce, and the cosmos will be ruled by shadows. In this era, black holes will emerge as the last architects of cosmic change, swallowing what remains of stars, planets, and even light itself. To follow the universe further into its future, we must turn our eyes toward these dark giants and enter the chapter where gravity, not light, tells the story. In the farthest stretches of time imaginable, every star will have burned out. The once fiery suns will have become black dwarfs, stellar corpses of carbon and oxygen, cooled until they no longer shine. They will be as dark as the space around them, detectable only by the faint pull of their gravity. Scattered across the void, these remnants will drift in silence, locked in slow orbits, or wandering alone. The universe will have lost its last natural light. The night will no longer be a backdrop for stars, but the entire stage itself. Over unimaginable epochs, the great structures of the cosmos will unravel. Stars, planets, and black dwarfs will be nudged out of their orbits by endless gravitational encounters, drifting into intergalactic space. The delicate web of galaxies will thin, its threads breaking as gravity loses its grip. The local group, once home to the Milky Way and Andromeda, will no longer exist as a coherent family. Every surviving object will be cast adrift, separated by such distances that contact or reunion will be impossible. In this dark emptiness, black holes will remain the final giants. They will feed for the last time on the debris of stars, the occasional wandering planet, or even each other. Yet even these titans will not endure forever. Through the slow trickle of Hawking radiation, their mass will seep away into the vacuum. For trillions upon trillions of years, they will fade, shrinking until, in one last pulse of energy, they vanish completely. The last great anchors of the universe will be gone. Before the final embers of matter fade, a strange kind of object may emerge: iron stars. Over inconceivably long spans of time, quantum tunneling may allow the nuclei within cold stellar remnants to rearrange, forming dense bodies made almost entirely of iron. They will not shine, they will not change quickly, but they will be monuments to the persistence of matter itself. Eventually, even they will decay, their protons succumbing to the slow march of instability until every atom is gone. When the last black hole evaporates and the last iron star crumbles, the universe will have no structures left. Protons will have decayed into lighter particles, and those particles will disperse until space is filled only with the faintest haze of radiation. The cosmic clock will still tick, but there will be nothing left to mark its passage. Time will continue without witness or event. The story of stars, galaxies, and life will be complete, and what remains will be a universe in perfect, featureless darkness. We live in a universe that is both ancient and young. Ancient because it has been expanding and evolving for nearly 14 billion years, carrying within it the echoes of its fiery birth. Young because its future stretches across unimaginable timescales, far beyond the length of human history, or even the lifespan of our planet. The stars we see tonight are not eternal. They are waypoints in a long journey, each destined to fade, each part of a cosmic story that began before us and will continue long after we are gone. We live in a universe that is both ancient and young. Ancient because it has been expanding and evolving for nearly 14 billion years, carrying within it the echoes of its fiery birth. Young because its future stretches across unimaginable timescales, far beyond the length of human history, or even the lifespan of our planet. The stars we see tonight are not eternal. They are waypoints in a long journey, each destined to fade, each part of a cosmic story that began before us and will continue long after we are gone. Over unimaginable epochs, the great structures of the cosmos will unravel. Stars, planets, and black dwarfs will be nudged out of their orbits by endless gravitational encounters, drifting into intergalactic space. The delicate web of galaxies will thin, its threads breaking as gravity loses its grip. The local group, once home to the Milky Way and Andromeda, will no longer exist as a coherent family. Every surviving object will be cast adrift, separated by such distances that contact or reunion will be impossible. Our place in this story is brief but extraordinary. For a fraction of cosmic time, we have the chance to look outward and understand the vast system we inhabit. We can measure the fading of the light, trace the birth and death of galaxies, and imagine the landscapes of the far future. We can see that the same forces that will one day end the stars are the forces that made us possible. This knowledge is not only scientific, it is deeply human, connecting us to a story written across the fabric of space and time. In the end, the universe will grow dark. Stars will go out, galaxies will dissolve, and the great structures of the cosmos will vanish into the silent expanse. But until that distant day, there is beauty to be found in every moment of light. To live now, in this thin sliver of time when the sky is still filled with stars, is to witness a chapter that will never come again. The universe is vast, but our ability to see it, to know it, and to reflect upon it is our greatest privilege. It is a reminder that even in the face of eternity, meaning is something we create in the here and now. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.